Hello, my name is Paula RESCALA, and I am an undergraduate student at Rice University. My research is devoted to crafting discretizations suitable for domain integration in mesh-free numerical methods. I would like to thank my mentor, Jacob Koester, for guiding me throughout this process, and I would also like to thank my sponsors, Sandia National Labs and the OREU program at Texas A&M University. In this presentation, I will begin by discussing the motivation for this project, including the background and the goal of the project. Then I will discuss 3 approaches I have attempted to achieve this goal, and finally, I will conclude with some conclusions and future work. This project requires the understanding that the finite element method is a powerful tool that has been used across disciplines for decades to solve all kinds of engineering problems. However, FEM has its drawbacks, and those are mainly due to meshing complications. For example, creating a mesh is just time-consuming, and so it's expensive to do. Additionally, when a mesh has to be created over a complex geometry, the problem becomes exceedingly difficult, and again, even more time-consuming to do. And the quality of the mesh cannot be sacrificed at all, since it is used for creating approximation functions and for domain integration. So the solution to all this that has been developed is the implementation and creation of mesh-free numerical methods. For example, the conforming reproducing kernel method is a mesh-free method because it does not need this discretization for creating the approximation functions. Rather, it is used solely for domain integration. The approximation functions are created on a point cloud, and so the quality of the mesh is not as tied to the quality of the solution as in FEM. So my project is actually to refine the meshing process and make it more effective with the goal that it will be suitable for these mesh-free methods. So to do so, I'm hoping to achieve this goal through an aggregation approach. So essentially what I mean by this is that we can just go ahead and take advantage of all the methods out there that are able to effectively create meshes, even though they may be of low quality. So for example, I will take a mesh like this one and recognize that it is a low quality mesh and thus still not acceptable to use since it has elements, like this one highlighted here, that are too thin and perhaps too small to handle, for example, large deformation problems. And the goal is to aggregate different elements in the low quality mesh and get a cluster of high quality as shown here. Now this one was handmade, but the idea remains the same. This can be considered a high quality cluster since it is nearly convex. It is very compact and has a rather uniform moment of inertia over both axes. So my first approach in aggregation work is to create a direct clustering algorithm, which I will go through step by step. The first step is to create what I call the seeds of the clusters, which will be the starting points of the clusters where each cluster consists of only one element in the mesh. And the point here is that I can create initial clusters that are equidistant from one another. To do so, I follow the maximal Poisson disk sampling algorithm, which is as follows. First, all elements are labeled as active, and then a random walk is done across all elements, and when an active one is reached, all elements within a predetermined radius are deactivated. This is the result. We input a mesh and a radius, and the output is the same mesh with equidistant seeds that are the starting points of the clusters. So the next thing to consider is that it may be easiest to just assign each element to the nearest cluster. But then the result is something like this. The edges are jagged due to the, in this case, triangular shape of the individual elements. This is undesirable. Instead, this result is actually used to set target areas for each cluster, which is important because the goal is to have clusters that are approximately the same size each. The way the algorithm works is that first the best cluster is selected to grow, and this is the one that is furthest from the target area. Next, the best element is added to the best cluster. The best element is chosen as the one that would minimize the heuristic function that I have here on the screen. So if you would like, you can go ahead and pause this video to take a closer look, but in general, this function is designed so that the lower the value, the better the resulting cluster, since it takes into account 3 different compactness metrics. And this function is defined for each individual cluster. So now here is actually the full outline of the algorithm. Just to recap, the first step is to select the seeds, and then it is followed by a process that chooses the best cluster to grow, and then the best element to add to this cluster, and it does so iteratively. The only other thing this algorithm takes into account is that once the mesh is almost completely full, it is possible that two clusters or more kind of fight over an element back and forth, and so the algorithm does not converge. So to stop this, I kept a deadlock list that would force the algorithm to continue if this should occur. Here's the result. So the positives are that the jagged boundaries are actually much better here. However, it is still not where I would like it to be in terms of cluster compactness. So from here, I moved on to my second approach. This approach is to create an integer program. So for the integer program, the idea is that the same heuristic function from approach 1 can be used. And instead of algorithmically coming to a result, I'll use optimization techniques. Here's the setup for the problem. There are three kinds of decision variables. The S variable is the most important because it will determine whether a given element will be in a cluster. So it's kind of like an assignment problem. The area and perimeter are technically needed to be defined as decision variables, but they are continuous. And also the result that will be used to actually cluster the elements once a minimum solution is reached is the S variable. That's going to be the most important one. Here's some parameters. Again, to get a closer look, go ahead and pause this video, but these are just for notation and kind of the notation I'm going to be using for the next part of the problem. So the rest of this problem is defined through the objective function and the constraints. So the objective is again to minimize the heuristic function from approach 1. I removed for now one of the compactness metrics because it would add unreasonable complexity in this problem, and I felt it best to start with something more easily solvable. In the constraints, all the basics are kind of taken into account. For example, the constraints on the left ensure that each element can only be assigned to one cluster and that each cluster has at least one element. And the constraints on the right define the area and perimeter, which are necessary for the objective function. So a drawback to this approach is that the program is both an integer program and it is nonlinear. This has made it extremely difficult to find a solver that can handle large problems with large meshes, which are much more realistic. Thus, for now, a result has not been found and different solvers are being tested. So I highlighted the decision variables here just to show that it really is nonlinear. For example, in the objective function, I have an area over perimeter constraint, and so this is nonlinear since area and perimeter are both decision variables. And in the perimeter constraint on the bottom right, also the S variable is multiplied by another S variable, so it's essentially an S squared term, which is of course nonlinear. Thus I moved into my final approach, which is using reinforcement learning, which is just a branch of machine learning. Reinforcement learning takes an environment, which in my case would be the entire mesh, and allows an agent to solve a problem on the environment. The agent is trained on thousands of environments until it learns a policy that will always find an optimal solution. So the agent knows that it's found the optimal solution when it achieves the highest reward possible for the environment. And in my case, it will be rewarded when all elements are in a cluster and when the clusters are of a certain quality, again measured with the heuristic function developed in approach 1. And I might have to make some adjustments to the heuristic function to take into account not only rewards, but also costs when the clusters are shaped poorly. And this will help the agent kind of learn a better policy that will optimize the solution in the end. And this is the newest approach I'm trying out. So I have no results quite yet since the training will take a bit of time. Again, thousands of meshes will need to be tested and trained, and the agent needs to be trained on thousands of meshes before it can actually effectively have a policy that will reach an optimal result. But the idea is very promising, right? So the agent will work on an environment, but actually only needs to take into account the local environment, which is the portion of the mesh that the agent should be able to see when making a decision, when making an action. So this agent is going to go and influence the environment by taking actions. For example, in my case, it'll be the agent can add a cluster or add an element to a cluster, or perhaps switch an element from one cluster to the next, and then it will either be rewarded or it will incur a cost. So thinking back to all three approaches, I have found that all approaches show promise in solving this aggregation problem that I have created. This is because they are all kind of moving towards optimizing a heuristic function, and all that is necessary is kind of refining the final steps in each approach, which of course are the most complex. So moving forward, the goal is to apply these approaches once they are refined to actual geometries. These are of course more complex, but since the approaches I developed all allow for various inputs, it should be a matter simply of translating a few parameters. And lastly, all my approaches will need to be translated into 3 dimensions, since most problems will require this, and this will make my solutions much more robust. Thank you for listening, and I hope you enjoyed.